Hello guys, welcome to our talk, Beating the Sanitizer, Why you should add MXSS to your toolbox. Now, my name is Yaniv, and today I'll be joined by my colleague, Paul. We're both vulnerability researchers at Sonar, mainly focusing on high-level code research, and we both really love XSS, in particular MXSS. Now, I hope that this talk will intrigue you guys into getting into this bug class and essentially adding it to your toolbox. So a small overview of what we will talk about today. We'll start with the background, just making sure we're all on the same page. And then we'll get into the technical details of MXSS. We'll showcase some real-life case studies of vulnerabilities that we found, and closing off the talk with mitigations and what the future holds for this bug class. So starting with the background, I'm pretty sure most of you, if not all of you here, are aware with the XSS bug class. But either way, let's just have a small recap. XSS is when an attacker has the ability to inject arbitrary JavaScript code into a vulnerable website. Thus, when a victim visits that website, they will execute this JavaScript code. And the most simple demonstration that we usually see is, let's say we have a forum website. Each user can just upload like a comment, and an attacker, instead of just writing hello world, they write hello and a script element. Now, if the forum does not handle this correctly, the user that visits that comment will just see hello, and the script will be embedded in the HTML, and the code will execute. And when talking about the impact of XSS, it could vary quite a lot. It could have no impact at all, but also it could have some devastating ones. It could have information leakage to account takeover, and even RCEs in some cases. Now, one major problem that forums could face is, let's say we do want to support some HTML features. We do want users to have a title or to have bullet points or images, etc. So we need to find a way to allow some HTML elements and features, but disallow the malicious ones. And probably developers will initially, the most common solution will be sanitizers. Now, sanitizers are actually meant to solve exactly this issue. They meant to take some HTML input and do some magic, and at the end have a clean HTML markup that is supposed to be safe to render. Now, if we take a look at what sanitizers do, they are not doing such a simple task. And they're not doing a simple task because in order to actually, in a smart way, understand the HTML and know what and how to change it in order to make it safe, they will need to parse the HTML. So from a string, they will need to have some kind of a structured HTML tree to know what to delete and how to delete it. And the problem that is HTML is parsing is hard. It's a difficult task, and mainly it's a difficult task because HTML is a tolerant language. And we can demonstrate it fairly easily by the following example. So we have a root element, and inside of it we have a comment tag. Now the comment is not closed here, and if we pass it along to the browser, we just see the hello, everything works fine. And when we look at the markup, suddenly the comment got closed. Also the root tag again. The parser just tries to fix the broken markup as close as possible to what the developer was intended. Now, if we take the same markup and we pass it along to an XML parser, for example, it would just be condescending and will tell us that the comment is not closed. Now, when you think about like how and why HTML is doing that, now the why is quite logical. Imagine every small mistake of a developer will just crash the whole website. We don't want that. And how it's doing that, luckily there's 1,500 pages long documentation on how to parse HTML. Unfortunately, when it comes to Sanitizer, it still leaves some open questions. Now, so we have a small background about XSS and also parsing. But what is MXSS? So MXSS stands for Mutation-based XSS, and mutation in HTML is any kind of change to the markup that is done for some reason or another. So what we saw right now, a broken markup that was fixed, that's a mutation. And mutation XSS takes advantage of this behavior in order to bypass the sanitization. Now, to start with the technical details, I will pass along the stage to Paul.
Thank you. Yes. So to talk about the different scenarios that we could encounter, we will first take a small overview. And actually, we lied a little bit. It's not all MXSS in the classical sense, because we also have some other bug classes. So the overarching umbrella term is more like advanced HTML sanitizer bypasses, but MXSS is shorter. So the first big group is parser differentials, which is where you have two different parsers. And they're either different because it's the same parser, but it's configured differently, or it's exactly two different implementations that just have differences in how they're coded and how they handle certain things. And the other big group is mutations. This is what Yaniv already mentioned, where the browser changes some stuff to fix the developer's mistakes. And it can either be the browser that changes this or the app itself. And we're going to first look now at parser differentials and then at mutations and then at the combination, basically. So for parser differentials, we take one step back to go to the usual flow of sanitizing stuff. So if you're a website and you have some user-controlled HTML that you want to sanitize, then you get the string, pass it to the sanitizer, and then the sanitizer passes it on to the renderer, which is the browser, and it then paints it onto your screen. But if we look at the sanitizer more closely, we actually see that it's 3 steps under the hood. So first, the HTML string has to be parsed into kind of a DOM tree structure. Then this structure is looked at by the sanitizer and all of the bad stuff is thrown out. Then it gets serialized back to an HTML string, which is then passed to the renderer. And also there we see under the hood, again, some parsing happens to take this HTML string back to the tree structure and then paint it to the screen. And as we see here, there's 2 parsing steps, 2 different ones. So this parser differentials category is all about what if these parsers work differently? Because if the sanitizer parses the HTML in one way and the renderer parses it in a whole different way because some difference, then it's like comparing apples and oranges. The sanitizer wouldn't really know what to do properly so that the renderer doesn't do anything bad. It's basically impossible. And as I said, parser differentials have 2 subcategories. One of them is the different configuration. So you have 2 times the exact same parser implementation. But for example, one has JavaScript enabled and the other one hasn't, or they expect different char sets and so on. And the other thing is you have 2 different implementations. One of those will always be in the browser because we're talking about XSS here. It has to be rendered at least once in the browser. And the classic other scenario is that your application sanitizes on the server side. So you have probably a parser and sanitizer implementation in a whole different programming language even that then sends the HTML string to the browser. So what does an attacker want to do if they find a parser differential? Again, sanitizers look for forbidden content, and one thing they usually never touch is raw data, because it's just raw data. It's not an HTML element, it's not JavaScript, so why should they throw it out? So it's the ideal place for an attacker to put their payload into, and then if they find a differential where maybe the renderer handles it differently than the sanitizer, maybe this hidden payload is not raw data anymore, but maybe an element. So in HTML, there's multiple ways how to put raw data in there. One thing is raw text elements, which we're going to look at more in a minute. The other is just comments, but sanitizers usually throw them out because they're not rendered anyways. Then we have attribute values, and finally C data, which stands for character data. So for these raw text elements, you can see on the left a screenshot from the HTML specification where it's all specified like, okay, this element should be parsed in this way. And all of those are parsed in some kind of raw data stuff. So on the right, you see an example, a style element. And as you can see, inside of the closing and opening and closing style tag, stuff is just parsed as text. There's no h1 child element. It's just the text. And also the opening comment token is not really starting an HTML comment. It's just text. So let's look at one other raw text element, which is no script. And this one is interesting. In the spec, it is said that basically this element is parsed differently depending on whether or not JavaScript is enabled. So if JavaScript is enabled, it's parsed like the style tag we just saw. So everything in between the opening and closing tag is just raw data. But if JavaScript is disabled, then we suddenly have a child element with an attribute that's also been closed by the browser. So there's definitely some difference here. But how could that go wrong, right? So this is a cool example of how it can go wrong. This is an example, or a real vulnerability found by Masato Kinugawa, an XSS legend. And basically, one day he was trying to Google for some XSS payload to find some stuff. And then suddenly the alert popped, which was not expected by him. And let's look into how that went and why that happened. So on the left, we see again our sanitizer steps. So first of all, this was his search query, an opening no script tag, and then a p tag with a title attribute with some innocent data inside the attribute value. Nothing suspicious here. So the sanitizer, which in this case had JavaScript disabled, parsed it like this, like an element. So inside of the title attributes value, there's some data, but it's just data. So the sanitizer doesn't do anything and passes it on to the renderer. And in the renderer, of course, JavaScript is enabled, like usually in the browser. So there it's parsed differently. And now we can see that the closing noScript tag that was previously hidden inside the title attributes value is now actually closing the noScript tag so that the image tag appears. And with that, the onError handler that then triggers the alert. And yeah, there were also other sanitizers and parsers that handled noScript elements in the wrong way. I mean, it is technically right if you look at the HTML spec, but they should reflect what the renderer will do. So they basically had to act like JavaScript was enabled. And yeah, we reported these and they were fixed. And now I handle it properly. So next to this configuration difference, JavaScript enabled or not, we can also have different implementations. And one example here is also the two parsing algorithms that are specified in the HTML specification. You might think there should only be one, but actually there's two. So one of them is the document parsing algorithm, which is used whenever you, for example, get HTML in the response from a web server and you just want to parse the whole document with a head, body, doc type, and everything. But sometimes you just want to parse a small subsection, a few elements that you just want to insert into an existing document. And that's where you would use the fragment parsing algorithm, or that's what the browser uses. And of course, this has to be context dependent because as we just saw, inside of different elements, things get parsed differently. So this fragment parsing algorithm has to know where the result will end up in. So if we use the inner HTML attribute to let the browser parse some HTML and we do it on a div tag, then we can see everything's parsed normally with normal HTML child elements being inserted into the div tag. But if we do the same thing on a style tag, then the thing that we already know happens. Everything inside the style tag should be raw text. So the parsing is in the raw text mode and just puts the text into there. And this could also go wrong if a sanitizer doesn't know where sanitized HTML will end up in, so that it parses and then sanitizes stuff wrongly. So this was the part about parser differentials. And now Yaniv's going to tell you about mutations.
Thank you, Paul. Yeah, so getting into our second scenario. So Paul just demonstrated what could go wrong if we compare apples to oranges. Now, I have a different question. Can something go wrong if we compare apples to apples? Well, the answer is yes. And the answer is yes because of something that's called parsing round trips. And actually, parsing round trips is a well-documented, well-known phenomena. Actually, the image that you see here is directly from the specification. And this behavior goes like this. They say that if we have an input and we parse it, we take the output of the parser and we parse it again in the same parser, the second output is not in particular the same one to the first one. So depending on the amount of time that we parse the HTML, it could just change. And yeah, so before we'll get into actual example of parsing round trips, let's just take a step back and have understanding of some nice HTML features. The major one is different namespace. So in HTML5, I think it was 2014, they implemented foreign content elements. Particularly, I'm speaking about the SVG and math elements. And they implement different namespace. And for the context of our talk, different namespace means different parsing rules. And we can very simply demonstrate that by using a style element. So here we have a style element, and the content of it is raw text, as just Paul described. Nothing fishy here. But if we take the same exact style element and we put it inside an SVG, suddenly we do have an A element inside of it. And again, that is because the namespace of SVG is different, and thus the parsing is different, and it just acts in a different way. Now, for those of you who are familiar with XML, you can think about the parsing inside SVG or math as closer to XML. So from now on, we will just add the prefix of the namespace itself in yellow. So you can see the first one is in the HTML namespace, and the second one is in the SVG namespace. Okay, so we have different namespaces, different parsing rules. But there's also a thing that's called foreign content breakers. So those specific HTML elements that you can see here on the screen are actually called foreign content breakers, are not allowed to be inside a foreign element. And in fact, if we do try to put them inside, you can see on the left, the P element is a foreign content breaker. When we parse it, the P will just break out of the SVG. On top of that, it will take all the elements that comes afterwards. So speaking about the P tag, one small quirk about HTML, P and break row BR are the only elements that could be created from an end tag. So here we have the end P and also end A. You can see that only the end P is created. Okay. So finally, we can get into our first example of a parsing round trip. In fact, this example was a bug in the specification, and when it was fixed, it was also enrolled to all the major browsers. So currently it's not this situation, but I did see some sanitizers that still parse it this way. So, yeah, it's still something to note. And the parsing round trip goes like this. We have an SVG element, and then we close a P tag. And initially, when we parse it, the P element will actually be inside the SVG. And then, when we serialize it, the P element was fixed. So we also have an opening P tag. And then when we parse it again, the P tag will just go out of the SVG and will change also the namespace. So what an attacker can do is simply add after the P element a style element. And initially it will look like this. We'll have a P and then a style element, which is currently in the SVG namespace. So the content of it is rendered as HTML, as tags, sorry. And you can see an A tag and then the title, and inside of it you can see our sneaky little image element. Yeah. So then when we reparse it, of course the P is fixed, and then the P execute the SVG, and the style also changes the namespace to HTML, and the content now is raw text. And when was our attribute, now is closing the style tag and creating a new image tag that wasn't here before. So I hope I didn't lose you guys in this example, because now we can go a little down the rabbit hole and we can talk about some more fun stuff about HTML. So I just described to you how we can implement different namespaces in HTML. What we can do as well, we can have HTML back to our different namespaces, and with something that's called HTML integration points. So those are the elements that you can see here for math and also correspondingly to the SVG. And basically, if we put those elements inside our math or SVG, the content will come back to HTML. Here you can see the M text, and then the descendants of it will come back to HTML. So we can basically have different namespaces and integrate them one within another. Okay. One last quirk, I promise. mglyph and malign mark. Two funny tags that parse in a funny way. So they say, we're talking about the math namespace here. Only if we are a direct descendant of an HTML integration point, we will keep the math namespace. So you can see in our example, we have math, and then we have an HTML integration point, mtext, and then we have an A element. And the first mglyph is not a direct descendant of the mtext. So it will be an HTML namespace. But the second one, because of it's a direct descendant of the mtext, will keep the math namespace. So let's take a quick example of our second parsing round trip. And the second one uses the form element. And this one was taken from the specification. You can see it's written no for element descendants. So basically you cannot nest form within a form. Funny enough, if you just continue reading the specification, they by themselves give an example of how you can nest form within a form. in the section of the parsing round trip. And this example goes like this, again, taken purely from the specification. So here we have an outer form, and then we have a div, and then closing form, and another form inside of it. And for some reason, if you put that input to a parser, initially you will have a nested form. But then when you reparse it, the second form will just get deleted. Now, maybe some of you connected the dots. Here we can have a form that on the second parsing trip, it will just get disappeared. And beforehand, we had elements that changed its behavior depending on the direct parent. So we can have this crazy looking XSS payload. Let's just parse it to have a better understanding of what's happening here. We have a form, and then we have a math, and inside of it we have an HTML integration point. And in that HTML integration point, we have a form, a nested form, using a similar technique to what we saw before. And then we have an mglyph. Now, the mglyph is not a direct descendant of mtext, so it is in the HTML namespace. And subsequently, also the style. And the content of the style now is raw text. But when parsing it again, the form is deleted, the mglyph is a direct descendant of the mtext, and the style is also coming back to the math namespace, and the image tag suddenly wasn't here before, but now it is. Now, a small disclaimer that the examples that you saw in this section was initially discovered and disclosed by Michal Bentovsky, a great researcher. Highly recommend you guys go read his blog, see his live stream. Following the publication of this this technique, we also disclosed various others, namespace confusion to other sanitizers. And the third and last scenario that we will cover today is what we like to call desanitization. And desanitization is when an application takes the output of the sanitizer, and then after this sanitization is done, interfere with it for some reason or another. As you probably saw, HTML parsing could be like unique, and if you change it just a bit, it could have a huge impact on the final DOM tree. So it basically means let's take the hard work of the sanitizer and throw it all to the garbage. And in fact, it's way more common than we anticipated. It's something that for some reason a lot of applications do. And we will show you some real life example in a bit. But before, let's take a look at a more simpler example. The first one uses Joplin, which is a note-taking app, desktop app, written in Electron. It has every attacker's wet dream. It has these unsafe configurations. And for those of you who are not familiar with the Electron, basically means that an XSS on the main window is equivalent to code execution. Now, the problem of Joplin is when they sanitized it, they used HTML parser too. So for those of you in the back that cannot read, or others that don't speak English, they write themselves in the description, if you need a strict HTML spec compliant, have a look at parse5. So they even say, we're not spec compliant, we're just a fast parser. And in fact, it was pretty easy to understand what they mean by that. They basically don't support foreign namespaces. So we can have this simple payload that for them will be raw text, but for Electron will actually be an element. So we can just add the on-air event handler, and we'll have the calculator pop up. They will see it like that, just a raw text, right? Nothing wrong. But then in the Electron, it will look like this. In fact, when we reported this vulnerability alongside other vulnerabilities, we were notified that it was also found independently by a different researcher, so kudos to them. And now we'll take a look at the example. And Joplin very conveniently has a feature to open a notepad from a link, so we'll use that. So here we have the link, and we'll open in Joplin, and we get a calculator. Thanks. Okay, our second example, MailSpring. MailSpring is an email client app. Also, again, written in Electron, has some really good red flags, not following some like security measures of Electron. But when taking a look at the green flags, when sanitizing, they do use DOM parser. So it shouldn't have a lot of parser differentials. DOM parsers, for those of you who are not familiar with, it's the built-in parser within our browsers and Electron. And yeah, they also implement different various security measures like CSP, sandbox, whatever. So when we initially took a look at this application, we were interested in how they sanitize HTML bodies to our emails. So we sent this one, and we found out funny things that they did. Actually, when they parsed it correctly, as we should all expect. It was using DOM parser. But during the sanitization process, they said, no, we don't allow SVG. And instead of just deleting the SVG, they decided it's smart to rename it. So they renamed it to span, and they did not reparse it. So everything still looks like this. But then, yeah, some of you already noticed that if we reparse it, everything go back to HTML namespace, and suddenly, again, we have an image tag that wasn't here before. And this one only sparked a huge chain of some bypasses and some other bugs in order to get an RCE. And if you're interested in the technical details, feel free to take a look at our blog. And I mean, worst case, if you cannot scan it now, just search online Mainspring and Sonar or speak with us. And yeah, now we can have a demo. So even though I did not explain the technical details, I will try to do my best. So here we have a Mainspring on the vulnerable versions. On the left here we have an attacker server. On the right we have a script that just sends an email. And initially we send an email with the malicious file in it, and also with some sneaky CSS exploitation technique. So this malicious file that we just sent was saved in a temporary folder on the machine, and we leaked now this path of the file. Yeah, so this is the path. And now we can use this malicious file that we uploaded to the victim's machine into our MXSS, similar to what you saw just before, and send the second email. Now, when the victim receives that second email, and they will try to reply or forward that email, I mean, you can guess what happens.
All right, the video's over, so we switch back. Well, that was a nice demo. We have one more for you, the final one. And this time it's in Proton Mail, which I'm sure a lot of you know or maybe even use. It's also an email service. This time it's end-to-end encrypted, and you can use it in the browser. So again, of course, they have to be very careful with the HTML that's coming inside of an email body to not have XSS in there and to keep it away from the actual Proton Mail app. So when we looked at their sanitization logic, it was kind of similar to Mailspring. They did use a good sanitizer, DOM Purify, but then they did something on their own after the sanitization step. So they went through all the sanitized document elements, and they looked for SVG elements, and again, they renamed them. They created a new Proton SVG element and moved all the children and then replaced the old element. And a little bit of foreshadowing, we now know that that's not the best idea. So going back to the sanitizer diagram, we now have this new step. And this is the desanitization vulnerability because, it just takes the hard work of DOM Purify and puts it to the trash if we put in the right payload. So here we use this payload, again, an SVG tag with a style tag, and inside an A tag with an innocent looking attribute. Then DOM Purify parses just like this because it knows the spec and parses exactly the same, and nothing suspicious, so nothing is thrown out. And then the renaming happens. And Proton SVG is now the outermost element, and then it gets serialized back to an HTML string and passed to the renderer. And there, of course, stuff's parsed differently again. And just a quick side-by-side comparison. On the left, we see the SVG element, and everything is parsed correctly to the SVG namespace. And on the right, we have Proton SVG, and somehow things are parsed differently. And of course, now the closing style tag prematurely closes, the style element and the image tag appears with the JavaScript. And of course, that is because renaming the element again changed the namespace, and then the reparsing later triggered the parsing differential or the desanitization. And this only started also a long journey of exploitation beyond that. You can also read a whole blog post or watch a talk about that. But I'm still going to show the demo. Of course, this is just a video because this was 2 years ago and ProtonMail fixed this. So on the right, you see the attacker who's starting their script and sending an email to the victim, which you can see logged in on the left. And when the email arrives and the victim refreshes their inbox and just views the email, nothing happens yet, nothing suspicious, some text, some image attachment, nothing bad. And on the right, the attacker script detected it and sent a follow-up email. And now if the victim just watches this one, the XSS triggers. Okay, now we know everything's broken, we are doomed, HTML was a bad idea. No, of course, there's mitigations and ways to do it right. So we want to give you some ideas how to do that. So first of all, if you don't need them, just avoid foreign content at all. No SVG, no mathml, because this removes a text surface. We've seen in almost all of the exploits we've shown you the use of some quirks of the foreign namespaces. So if you can handle this removed functionality of not supporting SVGs and not supporting fancy math markup, then just avoid them. And of course, don't do it by just renaming an SVG element. We've seen in ProtonMail and also in Mailspring that that's not the best idea. But instead, you should tell your sanitizer, which hopefully is DOM-Purify, to just support only HTML namespace elements, and you can do it like this. Then another good mitigation idea is to always encode HTML entities in raw text. As we've seen, you can a lot of times hide your attacker payload in raw text that then appears later. So if that raw text in an attribute value or in a raw text element would have been HTML encoded so that the ankle brackets are encoded properly, then no matter how different the parser later is, it's extremely unlikely that it would parse them as actually the starting ankle bracket of a tag. And this is also why Bleach and Sanitize HTML and others took this approach. So this is something that the sanitizer wants to implement and not the application. But you have to be a little bit careful because it might break styles, because inside of style tags, which is a raw text element in the HTML namespace, the CSS engine will not HTML decode stuff. So if you have some ankle brackets in there, they will appear as encoded in your CSS. So beware of that. But just to show you how all of this would look like, on the left we see the old style, and as you can see in the alt attribute, for example, there's a hidden style tag. But now on the right, if everything's encoded, then it's very unlikely that a parser would say, there's a closing style tag, let me use that. All right, another mitigation, again for sanitizers, is to do namespace checks. And this is basically when you really want to support SVG and mathml, like DOM-Purify. Then you have to check for each element if the element itself is supposed to be in the namespace that it's in. Because if not, then something fishy is going on, some mutation probably, so you want to throw it out. And also for HTML and foreign namespace integration points, you want to do also a check basically where if the element has a different namespace than its parent element, it can only be a handful of elements that are allowed in this situation. So you should throw them out if they're not those elements. And this is actually implemented by DOM-Purify. And so far it seems robust. I think there have been some mutations found that the browser does, that we, for example, saw with the form element, where this mitigation then explicitly saved DOM-Purify from a bypass. And the final one is, if you can, just avoid reparsing at all. This would kill two birds with one stone. You don't have browser mutations and you don't have parser differentials if you only parse once, because the mutation happens in the serialization step where you put it back into an HTML string. And if you parse once, then there's no parser differential. And instead of getting an HTML string, you just get a full DOM tree, DOM structure. And then you can directly insert it into your page. And with DOM Purifier, you can do it like this. You just set return DOM to true, and then you get a document instead of a sanitized string. Okay, now that we know not everything is doomed, maybe we can see what the future will hold for this topic of MXSS. And for the first thing is that we want to influence the future by creating an MXSS cheat that we published. So if you're a researcher or you're just interested now in HTML parsing and MXSS, you can go here and read on all the HTML quirks that we collected there. We also have payloads that led to bypasses in the past, and tools and write-ups and links, and also the credits of the researchers that found them, and also a bit about remediation. So you can go there and it's hopefully your one-stop shop. And if something's missing, then please contribute. It's on GitHub, so we can make the cheat sheet even nicer to elevate the MXSS research for the community, so you can find more bypasses and in the same time make sanitizers then more secure. And the other thing is that there's also stuff happening on the specification world. So in this case, the Sanitizer API is a new API that browsers want to implement or have already started so. Firefox already has it behind a feature flag, and Chrome added it and then removed it because it's not finalized yet. But basically the Sanitizer API is what all the sanitizers do, but it's just in the browser. So you don't have to bring your third-party dependency, DOM Purifier or whatever to do it. And you also avoid parser differentials and reparsing, because instead of first parsing and sanitizing something and then giving it again to the browser, you just tell the browser, hey, please render this weird HTML, but while doing it, skip all the bad elements, and then the browser does it for you. And another good thing about this is that it's context aware, so the browser knows where the result will end up in the document, in which namespace or in which raw text element. So it always knows which parsing and sanitization rules to use. So this is very promising. And then there's also stuff going on the HTML specification side. Some people proposed, for example, to always encode these angle brackets not everywhere in raw text, but in this case only in HTML attribute values. And Chrome already implemented this, and it already basically prevented or killed some of the payloads that we saw earlier, at least in Chrome. Because, again, the top line is where you see the hidden closing style tag, and the bottom line is just as the mitigation I showed, where it's encoded. So if then, depending on how the later parser is configured or in what state it is, in the top line, it would still maybe use the closing style tag as the actual closing tag for the opening one. But in the bottom, you see there's no way that it would parse it differently. Okay, let's wrap things up and draw some conclusions. First of all, we can say XSS is definitely not dead. Maybe it is dead in the case where you just encode everything and don't have to support any HTML. But if the application wants to support some of the HTML and not other stuff, then you just need to bypass the sanitizer. And as you've seen, that's super easy now. Then we want you to take away that backend sanitizers are inherently error prone. We talked a lot about the client side and how stuff is broken there. But basically, if you sanitize on the backend, you will always have a parser differential because I guess no parser implements the parsing just exactly like the browser. And of course, also the browsers differ a little bit between each other. So if you can, please prefer to sanitize on the client side. And right now you want to use DOM Purify for that. And in the future, hopefully you can use the Sanitizer API. And finally, we saw that defenders are on it. And in the future, we will hopefully get some improvements that remove some of these bugs. Thank you. And I think we have time for some questions. But I don't know where the mic is. The mic is coming.
Hi. So thanks for the great talk. I thought of another mitigation, but I don't know if it's possible to output when serializing to do less ambiguous output, just like with the ampersand LT semicolon and things, to explicitly output namespaces where it might be confusing. Is it possible?
Yeah, good idea. So it's basically like what XML does, I think. There you can have namespaces. I'm not entirely sure if it works the exact same in HTML, but I guess not, because otherwise probably some of the good sanitizers like DOM Purify would have done it already. But yeah, good idea. I'll look into it if that's possible.
Okay, thanks.
Any other questions? All the way in the back.
Thanks a lot. Very interesting topic. And just remember that Mario Heidrich has pronounced that cross-site scripting is dead like 7 years ago, probably, but still seems alive and kicking. My question is, these techniques and these patterns, how much would they be applicable to the web application firewall?
It depends, I would say. In my opinion, web application firewalls, you can always find a bypass if you just try long or hard enough. So I'm not sure if it's like the one thing you want to rely on. Of course, it can help to catch the known payloads and so on. But I guess an attacker that has enough time and motivation will always find a way to get around the web application firewall, and then you have the same vulnerability as before. So I would recommend fixing the vulnerability or the parser differential or whatever instead of trying to fix it with a WAF.
Totally agree. It would be just another interesting area for research, probably.
Yep. All right. Looks like we answered all questions. Otherwise, you can catch us later at the conference or at the CTF, and we'd love to talk about MXSS. Thank you.
Thanks.